Cool. Welcome to lecture 5. Today we're going to talk a little bit about objects in Python and do a short intro into algorithms and how to make things a bit more efficient with just our mind and approach. Okay, first thing, let's do objects in Python using classes. Classes are quite interesting in Python because they allow us to abstract things out. Say, let's have a look. First of all, we're going to implement noughts and crosses. So a simple game. But as we will dwell more into deeper into the topic, we'll see that it is actually quite messy and hard to implement straight away. And by abstractions, by maybe structurizing our ideas a bit better, we can make the thing a bit easier. Okay. All right. So the way we do objects in Python is that we define a class. We use the class keyword and then we name the class. Classes are really similar to types in a sense. They are types we define with our commands. But what distinguishes them from types is that they have different fields. They are not a single value. They can be a bit more complex. So in this case, we just define a class player, and it has two, we call it fields. So it has two kind of sub values. It has a Lloyd name and a symbol X. So Lloyd will be doing noughts in this game. So this is how we would call different things in a class definition. So we have a class definition, class name, then we have the variables, also called fields. And the way we instantiate an object, so we create an object, is that we assign a variable to it. So variable myPlayer will hold player object. Okay, and then we can change this name. So we can call him, for example, George. Yeah, and also retrieve the values from the fields in the object by calling the actual field in the object by the dot operation. So we have the object dot and then the name of the field. In this case, it will be name, but we could also check the symbol of the object. Yep. Then classes can also have their own methods. So functions, internal functions, also called methods, and then they can do different things with the object. As you can see, we also have to take into account the fact that self, so we're using the self keyword, self refers to the object itself. So when we're defining a class, we almost always have to mention that we're referring to some instance of an object to use this dot operation. And then also, if we're accessing different fields, different kind of sub values in this class, then we also have to use self dot something. We'll delve more into deep with the example. So again, the same naming. Okay, we have a method definition and method call. Methods are kind of sub functions of the class. Right. If we want to instantiate objects, but we want to set their fields on instantiation, so kind of if we don't have name equals Lloyd, we want to set it on creation of the object, we have to use the special method called init, and we define it with double underscores on both sides of the init keyword. This is a special method that creates the object with the given filled values. Okay, let's go into Workspace. Okay, there's some thingy. Let's just do this. Okay. Okay. So first, let's do a short recap with a recap with a different class, a doc class. And again, we're initializing it with the init keyword, and the doc will only have a name. So we will use self name equals name, and now we know that the field inside the dog object will be given by the value we pass into it. Okay, we don't have to write name here or declare it at any point. We'll do it in the initialize function. We also have a different class that sort of takes no arguments when we call it, like you can see here. But on the other hand, we need to pass in self, so we will need an instance of an object to call it. Okay, so we instantiate three types of dogs, three different dogs with different names, and well, we can either access their name or call the bark function. So one dog does woof woof, the other one does woof woof. There is no differentiation. All dogs make the same sound for now. And dog 2 has name Cooley. Okay. Now something more complicated with classes. So inheritance. Inheritance is a interesting property of classes, which allows us to kind of make parent classes. So make parents of a class something that is above or more general than the other object. So in the case of dogs, a dog is a very general concept. Different dogs can have different kind of specific attributes. They can behave in different ways. So we want to like create a subset of dogs, but still generalizing the subset itself. So, for example, let's say that the dog class is still the same, but we're introducing a happy field. So a dog can be happy. It has this extra feature. We just added to the general dog species. And we create a happy dog, which we say overrides, so has a different implementation of the make set function. So make set function in a regular dog would make it set. So it would set the happy boolean to false. But in case of a happy dog, we can't make it sad ever. It can be only happy. So we just say that we can't make it sad. There is an easy hack around this thing, because we can just do happy dog 1 happy false. Oh, sorry. Okay. And now you can see that it prints that you can't make me sad. But then if I try to print the happy status of the dog, then it will be false. So we kind of can tweak the internal values of the object by calling this dot operation on the different like sub values, the fields of the object. But we can't do it with a function. This is actually a small drawback of Python, that we can modify it in different languages like Java. We wouldn't be able to do it, or we could say that we don't want this to be possible. But in this case, we just need to remember to interface Python more with like setter functions, the functions that access the fields inside them. We shouldn't change the fields of the object on the go. So a small revision here, reiteration. We make a happy dog. We make a regular dog. We make the regular dog sad and just print whether it's sad or happy. We made it sad, so it will be sad. And then we make the happy dog sad. We try to make him sad, but we have this print statement over here that tells us that we can't make it sad. And they still bark in the same way. So happy dog inherits the bark function as well as the make happy function, but overrides the make sad function of the dog class. Apart from that, we can see that we have this super keyword over here. Super refers to the property that dog inherits from the dog. So the way we inherit methods from a parent class, in this case dog, is to including it in the bracket of the happy dog, so of the child class. And then we can use the super to call the init method without overriding it. This init statement is actually unnecessary because Python will on default call all super functions named the same in the parent class. But we can do it to just emphasize something or just, well, use the init, but then maybe add something to the name because it's a happy dog. So we can do like it's happy, right? And we can do HD. Right, to emphasize that it's happy. So we can both do the initialization from the parent method as well as from the child method. Cool. Well, different classes can have multiple parents in Python, but it introduces a lot of complication, especially with the super function. So usually if we want to inherit from some class, we should do it with just one parent class. Okay, another example is classes without the init, so without initializing the actual object. They can be thought of in simple terms as our own libraries, our own modules that are just a collection of functions. And then we won't use the self keyword if we're not really using the init operator. So for example, well, we have a complex number class, which is an actual instantiated object. That is why we're using the self operator here. And we have also a defined str function, which is used when we're printing a newly defined class. So if we want to print something in a nice way, like complex numbers, we also have to define the __ string function. But on the other hand, we have a class complex math, which will do basic operations on the complex numbers. And these basically take two complex numbers and do different operations with them. But each time we will do complex math, we'll have to call complex math dot and then the name of the method. In this example, we have two complex numbers. 1 plus I and 1 minus I, and we're adding them and multiplying them. And we can see that the printing is as follows. If we want to modify the string function, we can say that, for example, if the imaginary part is 0, we don't really care about the I component of the string, so we wouldn't include this part of the string. It's up to the person programming it. Okay. Coming back to knots and crosses or circles, whichever name you prefer. I also made a small example that defines a game class for playing knots and crosses. Because in the presentation, we just defined a player which had two fields. It had a name and a symbol. And now, having these two players, we would like to make them play, make them compete. First of all, we initialize the game with two players, player 1 and player 2. And we initialize the board, which is 3 by 3 empty-ish matrix. And we will also keep the track of the number of moves. Otherwise, we could also use whether player 1 or player 2 is playing a Boolean value. In this case, I decided to just keep track of the number of moves. Okay. So first is the play class of the game. So we will run the game for it to play. This is done by using a while loop. We'll have a helper function called isEnd, which will terminate the game. And by checking the modulus operator of 2, we're checking which player should play, whether player 1 or player 2. So they will do it. They will do their turns respectively. IsEnd is a bit verbose and not a really nice function, but I would like to show you something called duplication in coding, which is usually a bad feature of code, so we should avoid it. But this is the example of a code that is highly duplicated. So for example, we're checking rows over here and checking columns of the board to see if all of them have the same symbol. And if they do, then we will terminate the game and say that the particular player won. So first of all, these two double loops are really similar. So you might think of a way to kind of maybe making a different function that would just do the checking for us. Third, we check the diagonals, which is also really similar for both diagonals over here. This should also be avoided. So if you have an idea of creating a separate function for it, it might be a good exercise for you to try. So we checked all the rows, all the diagonals, and now we know that none of the players won so far. So it's either a draw or the game didn't really finish. So we're just checking whether there are any empty fields. And if there are no empty fields, then we'll just say that it's a draw. Finally, another function, makeMove, would just put the symbol on the specified coordinates given by the player. And a nice print board function that shows us the current state, the current positions of different symbols on the board. So we can try playing. Let's say we start from 1, 1, 1, and 1. So it puts the knot in the middle. All right. Now player A, which is the second player in this case, will put something in 1, let's say 0. Okay. Then player the first player will do 0, 1. right? Then the other player, let's say he doesn't see that player 1 is about to win, so he puts in 2, 2. And now we're in the winning situation, so we do, well, 2, 1. And we see that x1, our game stopped, and we implemented knots and crosses. This is kind of lengthy implementation, but we can see that even simple concepts can be a bit longer in code. Plus, this code has a lot of duplication in the is and method, so you can definitely make it, well, more beautiful according to your preference. Yeah, but all in all, we implemented a simple knots and crosses in Python. Okay, there are some exercises. Let me start with the first one. So we need to define an alien class that instantiates aliens with age equal to 1, and then increases the age by 1, calling the birthday method. Okay. Let's have a think about it for 1 minute, and then we'll start. Okay. So I hope that people watching later had a thought already. Let's start with defining a class, alien. And it goes through with init method. Remember to put the self keyword in the init. And we just initialize with age equal to 1. So we do self age equal to 1. Okay, cool. We also want to have a birthday method that will increase this age. Remember to put self, and we just increase the age by 1. Happy birthday. And that's it for this class. It's a really simple class. It just have an initialization and then the birthday. Cool. Now living aliens. So living aliens are a bit more complicated. So we need an is alive Boolean and consider dying function, which will just randomly kill some of the aliens. Yep, and also a reproduce function already given. All right. First thing we will probably want to do as we read the word random over here is that we will want to import the random module from Python. All right. Then we do initialization. And we do the same initialization as here, except we will also want to have a it's a live Boolean. And at the beginning, all aliens will be alive. We also want a birthday. Which is the same. We'll increase the age by 1. And now the consider dying function / method, which was probably the clue of this question. So we do self, also no arguments. And now we'll draw a random integer from 1 to 10 by random randint. And we'll check whether it's less than the age. Right? So the older the alien, the easier it will be for the particular alien to die. All right, and then it dies. So we set it is alive to false. One interesting thing is that we can still increase the age of the alien when it's alive. We might just not do it. So if, for example, not this, if the alien is not alive, then we'll just ignore the call to birthday because the alien is already dead. So aging is not a valid consideration. And finally, we just copy the reproduce method, which is the only method that actually returns something in our class. This is a bit harder example, so I already coded it up, but it is also the most fun. So first of all, we'll be simulating a population of aliens. So our object given by the definition we implemented. So first, we'll define some for loop that will make all aliens celebrate birthday. And some of them will reproduce, therefore, they will tell us whether they want to create a new alien. Also, aliens can reproduce, well, one alien can reproduce one alien, so they kind of don't do it in pairs, but it doesn't matter for our implementation. It's more proof of a concept. Aliens can also die. In case they die, then we don't want them to reproduce. We should remove the aliens that die at a particular time step and add new aliens to the population on reproduction. We'll do 100 time steps, and we'll print it with matplotlib, which we learned in the last lecture. Okay, cool. So we import the needed modules, random and matplotlib. We use the same alien class we implemented previously. And we start, for example, with one alien. I think it was not written in the spec, but yeah, we start with one alien. We'll see how it develops. So we have 100 time steps. I did it with just making a counter of aliens to add because there's nothing specific about when an alien is made. So at the end, I'll just add more aliens to the population. All right. The special factor in our simulation will be this number. So it tells us when the alien should actually reproduce. So if its age is, let's say, if it's young enough to reproduce. We'll see how the curve changes depending on this parameter. So let's say we're starting with this one. you can see that growth is clearly exponential. Let's do 5 over here, which will limit the reproduction a little bit. You can see that the population ceases instantaneously. Let's run it a couple of times. Oh, sorry. Ceases. Something interesting happens, but the population is not meant to live. The lower it is, it will probably just, die straight away. 6 appears to be the magic number, but not always. Sometimes it doesn't work. Sometimes we clearly get the exponential curve. It's quite funny because initially we start with 1 alien, and in case we have this exponential growth, we end up with 3,500. But we can see it's not always stable. Even 10,000 if it grows fast enough. Let's see what happens to 7. It might run for a while. We'll see if it terminates in like half a minute. Okay, we can see that the growth is really rapid because you can see that we have a for loop that loops over aliens, but all of them are reproducing really rapidly. So 7 takes a while to calculate, and it will be an exponential growth, even more rapid than the one with a 6 over there. Okay. Let's stop it for now. We just click the stop execution button and tweak it back to 6. And maybe let's leave it with a nice exponent. Hopefully it will become an exponent. Yeah, we have an exponent again. Okay. Now we'll do a last section of our course, which is a short introduction to algorithms. More so giving you an idea of some nice concepts that computer scientists came up with throughout the development of computer science. Okay, let's dig into it. So first approach is divide and conquer. It basically states that each problem can be divided in smaller sub-problems. Not all of the problems we encounter have this feature, but some, like searching a sorted list, for example, in our example, have this property that we can kind of reduce our problem into a smaller parts, and then just solve these smaller divisions, and then maybe with the solutions to the smaller divisions, receive the global result. First one is pretty simple. So it's called binary search. The idea is that we have a sorted list of elements, let's say numbers from 1 to 10, or a phone book. It's more down to earth example. And we want to find an element with a particular value in this sorted list. The thing we can do is look at the middle element in the list and see if it's greater or smaller than the element, and then proceed to the to the right half of the list, depending on the comparison between the middle element and the element we're trying to find. Okay. So now, if we go into the other half of the list, so one of the halves we started from, then we can basically just do the same search on the half, right? So we started with a whole list. Now we're reducing the problem into searching half of the list. And it will propagate till we actually end up with a list of length 0 or 1. So we're halving the search space on each iteration. Okay, so the algorithm works as follows. We keep track of the indices between which we're searching, and then we'll be looking at the middle element in the list. So first, if the element is greater than the middle element, then we'll just consider one of the halves. So we make low, this low boundary, equal to mid plus 1. Otherwise, mid minus 1. And in case the element is equal to the middle element, we straight away know that it's in the list. So we do, okay, it's in the list. Return true. Right? And this way we can do, for example, binary search of a list. This is an L, ls, and 2. Right? We can see whether 2 is in the list or 7 is in the list. This is actually an interesting algorithm because complexity of it is logarithmic. So if our list has n elements, then the number of operations we'll have to do, the number of checks to check if an element is in the list will be logarithmic in the number of steps we have to, in the number of elements we're processing. So for example, if we're checking 8 element list, it will turn up to be around 3 operations. It's way better than linear or quadratic algorithms, so it's definitely worth considering. Cool. Another algorithm that uses this idea of dividing the problem into smaller subproblems and then just leveraging the power that we have, the solutions to the smaller problems, is merge sort. So we want to sort the array to maybe search it binary afterwards, but first we want to sort it. So the simplest idea to do a sorting is to just take the minimum of a list constantly until we end up with an empty list, and insert the minima in order to the other list. This is what selection sort or insertion sort do. But there is another approach. So we can spot the fact that if the list is 0 or 1 in length, then it's for sure sorted. Otherwise, we want to divide the list into 2, sort the 2 elements, and then merge them so that the resulting list is sorted. It will be more clear in the algorithm. So first is the merge function. So we're receiving 2 sorted sublists, and now want to make a sorted list out of the 2. So if one of them is empty, then we clearly can return the other. Otherwise, we make a result. So we'll just take the first element from one or the other and just append it to the result. Right? We'll be using pop just to get rid of the first element of the list. Otherwise, if they were not of equal length, so if one of them finishes, then we'll just attach the elements of the other. And now merge sort is pretty simple. We're just checking whether the length is smaller than 1. This is our base case, because this is the recursive solution. So remember about the base case. And the other is the recursive case. So we're cutting into half and then just merge sorting the halves and finally merging them to one list. And we can see that it works quite well. We have list 1 to 3, which sorts to 1 to 3, and the other list that also ends up sorted. Okay, so divide and conquer, dividing the problem into subproblems, and then leveraging the knowledge of the solutions to the smaller subproblems. Other idea in computer science is dynamic programming, which is a fancy name for an approach that says that we can memorize kind of intermediate solutions to steps to get the general solution in faster time. The main idea is to reduce recalculating something on and on and on. We did Fibonacci implementations in our course previously, and this Fibonacci was calling itself twice. So it was fib of n-1 and fib of n-2. But now we can have a look the way the functions call themselves to figure out that this implementation, when we have two recursive calls, is actually exponential in the number of steps. So if we're checking the 30th Fibonacci number, it will take a very long time to calculate. So in this case, we have this inefficient Fibonacci algorithm, right? That just is very slow because, as you can probably see, Fibonacci of n-1 will call Fibonacci of n-2 in its body as well. And these repetitive calls, which lead to the same number, which we know the result to, are not really necessary. So we can memorize them. We say memorize them. So memorize the intermediate results. And this is the dynamic version, and also a faster version. So first of all, we don't even need to memorize all of the numbers we calculated previously. Just the last two calculated Fibonacci numbers will be enough. So we loop through, update the Fibonacci to the previous one. Given that the first two terms are 1 and 1, it can be 1 and 0, depending what definition of Fibonacci sequence you're using. And then it's just a linear algorithm. And we're just using two variables. It's a really tiny space. We say that space complexity, so the number of space that the solution involves, is constant because just two variables. If we're memorizing all of the values of Fibonacci numbers we calculated already, it will be linear in the size of the input, in n in this case. Okay, and we can see that, for example, brute force takes almost a second, whereas dynamic is so small that the time library doesn't even recall it. Around 90 seconds. 90, yeah, almost a second. It's also a good practice to, code a brute force solution so we can verify the results of the clever solutions, because it's easier to verify our logic in the inefficient implementation of Fibonacci. So then we can check our results by comparing it to the dynamic Fibonacci to check whether dynamic Fibonacci is actually a right implementation. Okay, another idea is greedy algorithms. There are two ways to approach greedy algorithms. So greedy algorithms in strict computer science are algorithms that solve problems that have, well, a feature that states that as we go to the solution, we just can take optimal local steps. So let's say we have an optimization problem. We want to pack objects in a school bag, and we want to take up least space we can. This is an optimization problem. So one way to approach this is to take the biggest objects at the bottom of the backpack and then just take the whole backpack. It turns out it's not the best solution always, but it's a good solution. So in natural sciences, greedy algorithms can also refer to approximate solutions to problems that actually take local optimal steps to receive a global optimal goal. Otherwise, greedy algorithms have this special mathematic feature, which is not really relevant here, that some problems actually receive the global optimal solution, taking the local optimal steps. We even have a proof of this feature here. But our idea is to cover the set of points with given length intervals. And one way to do it is actually sort the points we are given. So the points are on one line, and we want to cover them with the least number of length intervals possible. So we start with the first with sorting the points, and then we'll just basically make the beginning of the first interval where the first point starts, and it will cover the most possible points we can, because putting the interval before the first point wouldn't really give us any advantage. And then we just repeat the solution for other points as we go on. All right. So that was a brief overview of our algorithmic concepts in computer science, some main topics. All right, let's come back to the presentation. So if you're watching this later on, then if we're done our job correctly, then you probably have resources and idea about Python that will allow you to grow and learn further. In your own time, maybe doing your own coding projects or your own research work, you definitely have the fundamentals in this course that will be very useful in your first maybe serious coding project. And it's and these tools are basically enough to do most computer science based questions you'll ever tackle. Now it's basically up to you to practice. If you want to do more research-based physics, biology, plotting, then you also can visit the website of the Earth Sciences department. I shared multiple times, and you have also resources about Matplotlib, Pandas, and other libraries that are more for natural sciences researchers. Okay, that's it for the course. I hope you enjoyed it, and if you have any questions, please don't hesitate to email me or any of my colleagues. I would also like to thank you, thank DocSoc for organizing the whole course, for supplying the Teams channel, and yeah, thank you very much. We can stop recording and see you in the future.